Yeah, part of this talk was already given. So I imagine LUVOIR as being a giant telescope that we probably park at L2, so beyond the moon. It lasts for a century, right? It lasts for decades. And it is a serviceable. John, are you down to go to L2? Takes a couple weeks, right? Or you can do a lot robotically. But this is really a grand sort of vision. I think it's also, we should think of this not so much in isolation. I would really love to see NASA develop the idea of an L2 observatory where maybe NASA sets up the infrastructure. And whatever we do for exoplanets is one of the missions. I think the other studies, far infrared and the high energy missions should be done as well. But you can imagine then having China deliver an instrument or a telescope to the L2 observatory, right? And we can partner that way to actually all do more. So I'll tell you a little bit about what we've been working on with LUVOIR. And the first thing I wanted to talk about is the name, right? So you already heard Large Ultraviolet Optical Infrared Telescope. And when a lot of people see this, the name, they pronounce it LUVOIR, okay? Like it's French, all right? You pronounce it like a pirate, LUVOIR. Okay, so maybe we need to practice that as LUVOIR, all right? And so this is a space telescope in the tradition of Hubble that will last for a long time. It has very broad science capabilities. It extends from the far UV to the near IR band passes. I'll show you a little bit more about that through the talk. And when Paul Hertz asked us to study this mission concept, you know, he said, think about something in the range of a 12-meter telescope or a 15-meter telescope, but then I want you to tell me what we get scientifically if we put another ring of mirrors around this segmented telescope. So it's truly a grand sort of vision. We've been working on the types of instruments that we would have, and we think of this, as you heard, all new missions that of this sort of scope have to be serviceable. Okay, so we have to plan for that from the beginning, that the instruments can be upgraded. It would be the space observatory for the 21st century, right? An incredible way to answer questions that we haven't even begun to ask yet. And to sort of put this in context, imagine astronomy today without Hubble, right? How different it would be without these sorts of pictures that we have. And so that's what we're trying to imagine how astronomy will be changed when we go to LUVOIR. So here are some simulations. You see a hypothetical planet 9 on the left-hand column are the actual observations, the pinwheel galaxy. And then you see how these images would look with different telescopes. So with the Hubble Space Telescope, with a small HabEx or LUVOIR mission, a 16-meter telescope, and with something that's like, you know, 16, 18 meters in diameter. So size does matter. You can learn, this is a telescope that we envision will be for exoplanets, astrobiology, but will also serve the entire astronomical community. We'll be able to study better how galaxies form and assemble their first stars. So these rings show you, in some sense, the physical distance that we can go out into the universe, right? The Hubble Space Telescope has given us these unbelievable pictures of the deep field and early galaxies. JWST will be able to look a little bit further out. And then depending on the size of a LUVOIR telescope, 8 meters to 16 meters, will make the difference between being able to actually see a large number of elliptical galaxies, giant elliptical galaxies, and understand those. So LUVOIR will help us to reach out to 12 megaparsecs with incredible resolution. We'll be able to actually resolve stars in the galaxies at these distances. You already saw one of these images in John's talk, but the Europa jets observed with HST would have this kind of a resolution with LUVOIR. So we're imagining that this is a space telescope that also serves the planetary science community, people studying the solar system. And then the killer app for the AbSciCon folks here is our ability to use a coronagraph and take images of Venus and Earth and Jupiter-like planets orbiting stars. This is an example, a simulation of a solar system that's 13 parsecs away. And it has a coronagraph on a 12-meter telescope. So it's the kind of resolution and images that you can expect to see. We can then begin to take spectra of those dots if we can null out the light from the star. The inner working angle is about 4 lambda over d, allows us at 13 parsecs to be able to easily resolve Venus and certainly Earth in a solar system analog. So again, the biosignatures are really what we're after, right? You can imagine looking for Rayleigh scattering, but we also would like to be able to resolve oxygen, see if there's water vapor, see if there's methane coming out of the back ends of some cows on those planets. And this means that we have to look from 0.4 microns to 2.4 microns for the optical and near-infrared spectroscopy with a resolution of about 150. So a reality check is that this shows a spectrum of a modern Earth. And you see the wavelength range going again from 0.4 to about 2.5, where the error bars get very large because the thermal background from the telescope is so high. And if we looked at the Archean Earth, so we heard about this this morning, you know, maybe we're looking at planets that are habitable worlds, but they don't really quite look like ours yet. You'd still be able to resolve whether or not there are these important oxygen or O3 signatures in the spectra. So it allows us to have access to an incredible range of molecules, and that helps us to understand the atmospheres. We'll be able to see bands of oxygen, ozone, O4, H2O, carbon monoxide, carbon dioxide, and methane. And the key is that we'll have multiple bands of the same molecules. This is, for anyone who does spectroscopy, you understand how important this is to be able to have a secure abundance measurement. The broad spectral bandpass and the ultraviolet spectrum of the star can probably help us to rule out the false positive oxygen signatures, biosignatures that we heard about at the end of the morning sessions. And since the inner working angle with a large LUVOIR telescope allows us to see planets like the Earth at longer wavelengths, that will again give us more access to these incredible biosignatures. We've done trade studies, so there's another concept mission that's being studied, HabX. And HabX and LUVOIR, in some sense, are a continuum of science. Both missions want to look at biosignatures. Both missions want to have some cosmic origin applications. And it really comes down to a difference, I think, in the quantity of what we'll be able to measure. So with a 4-meter telescope, we'll hope to be able to detect something like 6 Earth candidates. When we increase the telescope size to 8 meters, the number goes up to about 25. And as we go up to a 16-meter telescope, we're talking about being able to detect with a coronagraphic imaging something like 100 Earth candidates. We think that this is important because it's likely that not every one of these Earth candidates will have spectral signatures, biosignatures. So if the frequency of habitable worlds is something like 10%, then we'd like to have something like 30 candidates, right, to be able to guarantee seeing one Earth analog signature with high confidence. I think the most amazing thing is I remember in the early days before Kepler was launched, right? And Kepler was going to measure eta sub Earth, and that was the most important thing, and that was the science goal that we were all focused on. And what none of us really imagined or thought about was what Kepler would really discover, this incredible zoo of exoplanets. What a mission. Like, would we have not funded Kepler if we would have known that eta sub Earth was going to be this hard, right, and thrown away all of this incredible science? So I think that's the kind of thing that we can expect from a large telescope that can collect spectra of exoplanet atmospheres. We're going to learn so much about what these planets are like. So there are some real observational challenges. First of all, to find faint planets sitting next to bright stars, you have to use a coronagraph. So the solution that we envision is an optical and near-infrared coronagraph with contrast ratios of 10 to the minus 10. That allows you to actually begin to see an exo-Earth. We would have multi-resolution spectroscopy, so in a bandpass over 0.2 to 2.4 microns. And this is technology development that's happening right now with WFIRST, for the WFIRST coronagraph. So a LUVOIR mission is going to be able to draw on the experiences of the space missions that are being built right now. Another problem is the ultraviolet. The ultraviolet is so incredibly useful for understanding the atmosphere and the conditions of habitability. We can't see the ultraviolet through the Earth's atmosphere, so our plan is an instrument which we're calling LUMIS. This is in the Instrument Design Lab right now at Goddard Space Flight Center, where we're trying to sort of go through the exercise of planning what this instrument would look like. So in part so we can figure out the technical challenges, and in part so that we can develop a cost model for the instrument. So this would, the LUMOS would do far UV to near UV spectroscopy. The PI for this instrument is Kevin France. Would do near UV imaging, and in essence, it would be a major upgrade of STIS on the Hubble Space Telescope for any of you who use that instrument. Another challenge is imaging very wide fields at high resolution. And so the solution to that is the high definition imager. Mark Postman at Space Telescope is leading this instrument as a sort of PI. The idea is to have a 2 by 3 arc-minute field of view. Again, it's an optical to infrared bandpass, and do incredible high precision astrometry. So Mike Shao has come up with an idea of using a couple of single mode fiber fed lasers to calibrate at the level of 10 to the minus 4th the pixel positions and to actually measure exoplanet masses. Another challenge is actually measuring the molecules. So here we envision an optical near-infrared spectrograph. Courtney Dressing is going to be leading this study. We'll have multiple resolutions, nominally about 100,000. And this will allow us to have very high photometric precision for transit observations. We're not sure, but one of the other things we might do is have the ability to measure high precision radial velocities so that we can get masses of the exoplanets, and coupled with the spectroscopic measurements, we'll be able to interpret the data more reliably. One of our European partners in France is building Pollux, which is a UV spectropolarimeter, and it will work with the LUMOS instrument. And this is an example of a partnership with the international community. All of you are encouraged to go to the LUVOIR simulation page, where you can see, for different exposure times and different choices of aperture, exactly what kind of science you could get out of these missions. We're also encouraging you to come and give us some feedback. Right now, there's a tech team that's examining the technological challenges to LUVOIR. One of them, the deployment of LUVOIR, will be tested by the James Webb Space Telescope. There are other technical challenges. First of all, we're going to need a heavy launch lift vehicle, right, with a large fairing to be able to get the segments for a 16-meter telescope into space. We're working on compatibility of ultraviolet and the UV with coronagraphy, and high contrast observations and coronagraphy with a segmented telescope. These look like solvable solutions. This is, again, I'll go quickly through these slides, one of just 4 mission concept studies that are being done right now. There are 2 LUVOIR mission architectures we're studying. We're imagining an aperture size of 15 meters and one of 9 meters. And these are set because of the fairings that are available right now for launch vehicles. The study office and engineering team is at Goddard. And we've got a team of people, 24 STDT members in the community, and working groups studying all of these questions, along with 5 instrument teams. Here are the pictures of the folks. So often people ask, so I'll anticipate some questions right now. What is the difference between HabEx and LUVOIR? And we've worked together as a team to try and come up with an answer that we think will work, that we both agree upon. First of all, both of them have the science goal of measuring habitable planets and biosignatures. And both of them have the goal of doing broad astrophysics. It's really more a matter of quantity, how much you'll be able to do with the smaller telescope and the larger telescope. So similar goals, but different sort of quantitative levels of ambition for these two studies. And then finally, anticipating a question, how much is it going to cost? And the answer is we don't know. That's why we're doing the study right now, to try and get a sense of what this will cost. As John said, it's not straightforward to estimate or to extrapolate a cost for a large mission. I'll put our summary slide up here, that our primary goals are habitable exoplanets and biosignatures, but also a large range of fundamental astrophysics. Okay, thank you.